black hole can evaporate away an entire universe's worth of information. And yet, according to modern physics, information can never be destroyed. Stephen Hawking believed black holes really do erase information. Today, most physicists think he was wrong, and proving it forced us to rethink what a black hole even is. Imagine throwing your phone into a black hole. Classically, it's gone forever. But quantum mechanics insists that, in principle, every bit describing every atom of your phone must still exist somewhere. Hawking's original calculation said, no, the information is lost. That clash between Einstein's gravity and quantum theory became the black hole information paradox, one of the deepest puzzles in science, and the reason Hawking had to change his mind. To understand where Hawking went wrong, you need the basic picture. A black hole is what you get when so much mass is squeezed into so small a volume that escape velocity exceeds the speed of light. Not even light can get out, for a non-spinning black hole the size of this no-return boundary, the event horizon, is set by its mass. A black hole with the mass of our Sun would have a radius of about 3 kilometers. From far away, a black hole looks simple, just mass, spin, and electric charge. This is the no-hair theorem. All the messy details of what fell in, stars, gas, planets, your unlucky phone, seem to be wiped away, leaving only those 3 numbers. That apparent simplicity is what made Hawking's original conclusion feel so natural. If the outside only remembers 3 numbers, maybe the rest of the information really is gone. Then Hawking did something radical. In 1974, he asked, what happens if you take quantum fields seriously near the event horizon? Quantum mechanics says empty space is never truly empty. It seethes with virtual particle-antiparticle pairs, constantly popping in and out of existence, borrowing energy from the vacuum and paying it back almost instantly. Near the horizon, Hawking realized the intense gravity can separate these pairs. One particle falls in, the other escapes to infinity as real radiation. To a distant observer, the black hole is glowing with a faint thermal spectrum, now called Hawking radiation, with a temperature inversely proportional to its mass. A black hole with the mass of the Sun would be about 60 nanokelvin, tiny. But over unimaginable timescales, this radiation carries away energy. The black hole shrinks, heats up, and eventually evaporates. Here's the catch. Hawking's calculation said this radiation is perfectly thermal. It carries no imprint of what formed the black hole or what fell in. If you only see featureless heat, you can't reconstruct the original information. When the black hole finally evaporates, all that's left is a warm bath of random photons and particles. The detailed quantum state that went in seems destroyed. But quantum mechanics has a rule. The evolution of a closed system is unitary. That means information is never lost, it's only scrambled. If Hawking was right, quantum theory would have to be fundamentally modified. If quantum theory is right, something about Hawking's picture of black holes must be incomplete. This isn't a minor detail. It's a direct collision between the 2 most successful theories in physics, general relativity and quantum mechanics. Over the next decades, physicists attacked the paradox from every angle. One key idea came from black hole thermodynamics. In the 1970s, Jacob Bekenstein argued that a black hole should have an entropy, a measure of how many microscopic states it could be in, proportional not to its volume, but to the area of its event horizon. Hawking's radiation gave this entropy a precise formula, area divided by 4, in Planck units. That area law hinted that the information isn't stored in the interior at all, but somehow on the horizon's surface, like bits on a cosmic hard drive. Later, string theory provided explicit examples. Certain kinds of black holes could be built from vibrating strings and brains, and you could literally count their microscopic states. The result matched the Bekenstein-Hawking entropy. That strongly suggested the information is still there, just encoded in an insanely complicated way. Then came a deeper twist, holography. In the late 1990s, Juan Maldacena proposed the AD-SCFT correspondence, a duality between a gravitational universe with black holes and a lower dimensional quantum field theory living on its boundary, with no gravity at all. In that boundary theory, evolution is manifestly unitary. Information never disappears. So if a black hole forms and evaporates in the bulk universe, the dual description guarantees the process preserves information. In this holographic view, a black hole is like a projection of some more fundamental quantum system. The no-hair simplicity is an illusion of low-resolution observation. Up close, the horizon is a seething quantum-entangled surface with an astronomical number of internal configurations. Hawking's original calculation treated the horizon as smooth and featureless. That's where most physicists now think he went wrong. He missed the subtle quantum correlations that would let information leak out in the radiation. But fixing Hawking's mistake created new problems. In 2012, the firewall paradox appeared. If information escapes in Hawking radiation, then late-time radiation must be entangled with early-time radiation. At the same time, quantum field theory near the horizon says outgoing particles should be entangled with their partners falling in. You can't have both kinds of entanglement at once. Something has to give. One radical proposal says the event horizon isn't smooth at all. Instead, it's a firewall of high-energy quanta that would incinerate anything falling in, violating Einstein's equivalence principle. Others argue that space-time itself becomes non-local at the horizon, allowing information to be subtly teleported out without drama. Ideas like soft hair, extra quantum charges on the horizon, and EREL-EPR, a conjectured link between wormholes and entanglement, are attempts to thread this needle. None are universally accepted. So where does that leave Hawking? By the end of his life, he conceded that information is probably not lost, and even proposed that subtle fluctuations of the horizon, his version of soft hair, could encode it. But we still don't have a complete, experimentally tested theory of quantum gravity that shows exactly how the information gets out, particle by particle, as the black hole evaporates. The biggest open question is simple to state and brutally hard to answer. What is a black hole, really, at the quantum level? Is the event horizon a smooth membrane, a tangled web of microscopic degrees of freedom, or something we don't yet have the language to describe? Whatever the answer, it will reshape our understanding of space, time, and reality. And that's the kind of mystery we live for on Terra Nova.